I'll start. Thank you for coming. My name is Jules May. I'm making a pretty good claim here. And that's why you're here. You want to see if I can deliver on this. Yes, I can. I have made a discovery, and I ran up against this quite by accident. I was working on some software. We had a number of products, but we had two very large ones. We had one product which was about 2.5 million lines, which had been developed over about 5 years by this growing team of people. And we had another one which was rather smaller. It was only about 1 million lines. There were mixtures of code. One was mostly C#, a bunch of things all through it, and the other one was VB. As you can imagine, we were dogged with reliability problems. We had terrible bugs. We didn't understand why. And so I decided to find out where our bugs were coming from. So we surveyed this code base. What we were looking for was an understanding of the defects and the way they caused the bugs that we could find in the code. So the process that we looked for was we found the bugs that had been reported, and we went back to the fixes that had been made in response to those bugs, so that we could see what sort of the cause of those bugs were. And then we categorized those bugs according to the nature of the fix. So some of these problems would have been caused by people simply not understanding the specifications. Some of them were caused by typos, that kind of thing. Now this is what we found. And this was a complete surprise. We found that over 90% of the fixes to the bugs that we found were of a single type. Basically, 90% of these bugs, over 90% of the bugs, were caused by one single repeated anti-pattern. And I was amazed. I was thinking, how can nobody know about this? But then we looked in a little deeper. And what we found next, we classified bugs into two types. We said some of these defects are bugs that are caused by problems in the code. These are genuine bugs. These are what we call first generation bugs. But then other bugs have come out as a result of the previous fixes. And so we're trying to understand if there's a difference between them. Check this out. We found that about 90% of the primary bugs were of this type. And practically all of the secondary bugs were of this type. So basically what we're seeing is that all of our defects are here, and all of our code rot was here. And so the question is, can we categorize that? Can we spot it? Can we do something about it? The answer is yes, we can. So what is this anti-pattern? I'm going to tell you, but not right now, you have to wait. Here's what we're going to do. We're going to talk about what the problem is. We're going to talk about the nature of the anti-pattern. We're also going to talk about Goto, because about 50 years ago, Goto was figured in exactly the same way as we're figuring this, and they said Goto is the root of all evil, and we have to stop using it. We need to understand why. What's wrong? What's so bad about Goto? Right now, nobody knows. No, right now, everybody says, well, nobody would use Goto. It's horrible. But actually, there's a good reason, and we need to understand what that reason is, so we'll be exploring that. What we'll do next is we'll compare that with ifs. That anti-pattern revolves around ifs is the problem, but ifs is part of it. So we'll take what we know about Goto and apply it to ifs. What we'll then do is we're going to talk about how to fix that. Now, just to give you a bit of a preview, when we understood what was wrong with Goto, the fix with Goto was structured code. When we understood what was wrong with conditions, the fix is structured conditions. So I'm going to do, and that's going to be a large part of what we're going through. Now, we don't have languages that do structured conditions the way we have languages that do structured flow. But if we did, what would they look like? So that's what we're going to talk about. So that's going to be, that second half of the talk is really where the remediation is. So far, so good. I'm afraid the first part of this is going to be a bit theoretical. It's just in the nature of this subject. I'm going to take it slow. I know that most of you are not computer scientists, but we do need to cover a bit of computer science. So if you're not following me, stop me, ask questions, because it's important that we understand what we're talking about before we go to the next stage. Does that make sense? Everybody happy? Okay. We start with this chap, Edgar Dijkstra. Now, he was a computer scientist in the days before there even was such a thing as computer science. He was working in the Netherlands in the 60s, and then he went on to work at the University of Texas. Now, he wrote a letter to the communications of the ACM called A Case Against the Goto Statement. And in this letter, he did a number of things. He said, first of all, by looking at code, by looking at the reliability of code, by looking at the stuff that people produce, he says he found a correlation between the reliability of the code and the number of Gotos in a piece. So he said there is something wrong with the Goto statement. It's something which undermines reliability. He then went on to say why he gave us a theoretical foundation of what it was doing wrong. And he, in effect, invented what we now know as structured programming. This incident was in 1968. Now, in 1968, people were writing in Fortran. Dartmouth Basic was what they thought was a good learning language. Pascal was still a year away. There was no such thing as objects. Even Simula was still 5 years away. So we're talking about a landscape in which people's understanding of computation was very basic, very mechanistic compared to now. And what he did was he said, this mechanistic view it won't give us the kind of reliability that we want to create. And so he invented the structured programming backwards. Anyway, he sent this letter off to the ACM. And the editor of the ACM, who was called Niklaus Wiert, who was the chap who was responsible for Pascal, said, this is a great paper, you've got to publish it, but the title sucks. And so that was the other thing that he created the considered harmful trap. Now, why did he object so much? He said that we have a problem in our understanding, the way people think about things. It's not a mechanical problem, it's not an engineering problem. He says it's a psychological problem. His view is this, that what a program looks like is something which we can deal with. But what a program means is something completely different. And that difference in view, is where the problem stems from. So, he says, what a program looks like, when we look at it on the screen or we look at it on the page, it's static, it's a map, it's a layout. You start at the top, you move down, you have a sense of location. When you're looking at code, I mean, the language that you use, you put it to somebody and say, well, when do you get here? And your language is all geographical. But that's not what it means. What it means is something much more dynamic. What the program does is it orchestrates this dance inside the machinery. Sometimes it's an extremely complex dance, but the point is that what we're dealing with here is an inherently dynamic process. And again, you know this from the way you use your machine and the way you use language. You'll have a program running and then you'll stop it and you'll say, where have we stopped it? And you'll sort of translate into these geographic terms. And you'll talk about the status, you'll talk about the values of variables and what's on the stack and all of those sorts of things. Because while it's moving, it's not accessible to you. It's only when it's stationary that you can see it. This is a fundamental way in which people think. There's no way around this. This is just for themselves. We build computers because they think differently to us, but this difference is explored here. Okay. On the static map, the program itself, it has this sense of locations which don't move, they're static. In the running program, we have this temporal sense, this sense of movement, these sense of moments in time. Now, what Dijkstra did was he introduced this notion of an execution coordinate. He says that actually what we want to do is we want to find a sense of location which captures both of these ideas. Now, at that point, he didn't have this. So this is the real thing that he invented. And the structured code that we now understand is a consequence of this invention. But the execution coordinate, he says, should represent a location in space in the program. And the same coordinate should represent an instant in time in the execution. And he says if we could make one value, one thing, do both of those things, then what we can do is close the gap between what the program looks like and what it means. And at that point, we're now working with a more accurate model. We still don't understand the dynamism, but what we do have is a model which can represent it for us and effectively understand. So the key thing is, can we construct this idea of an execution coordinate? Does that make sense? Anybody want to ask anything there? Good. So let's have a look at what he meant by an execution coordinate. We'll start off with the really simplest, trivialist program that we can possibly have. What we're going to do is we're going to execute this program. But as we do, we're going to keep a record of it in time, like a sort of a photo finish. So when we execute it, each line executes, and we can see that for each line, there is an instant in time. It's quite clear what that instant in time is. And we can see that we start at the top and we've moved down to the bottom. So we can talk about line 14, and it can represent this location, but that same line 14 will represent this instant in time. So this is an example of where the execution coordinate is accurately representing the dynamism. It's not much dynamism there, I admit, this is a very simple example. But what we have is this idea of the line representing the instant in time. But look, we can commute these. Let's suppose this is going through an optimizer, and these lines are happening not in the order in which it appears, but they're still laid out this way. What will happen is these will commute, but we can still say that for each location, for each line, there is a corresponding moment in time, even if they're not in the right order. Does that make sense? The important thing is that they match up. Line 14 means this moment, line 12 means this moment. Now, let's execute that program again, and this time we'll keep a track of it. So here is our execution coordinate down here. So you store it counted up, we've now stopped the program, exactly as you used to do it. And this is not special, this is what you're debugging to now. You stop the program, and we know what line we're on, we know what instant in execution time we're looking at. So far, so good. Now we also can see that that's a function call. So when we call into that, we're going to start constructing a stack. So let's follow that call in. You can see this stack building up, you can see one call after another. And this, too, is part of his idea of an execution coordinate. The execution coordinate is a sequence of numbers representing each instant in time, one inside another. So what we've done is we've begun instant 30. We've started on line 30. We're now going on doing something else in some other lines, but we haven't yet completed it. And that's what this tuple represents. And again, this is absolutely familiar to you. This is nothing that you've not seen before. This is exactly what your debuggers are doing now. This is a perfectly ordinary call stack. So far, so good. Again, this idea of a call stack, the man invented it. You know what I'm married. Okay, let's finish that execution. It's done. So again, you've seen that for each instant in time, we have a unique execution coordinate. If we'd had two different print statements, then we'd have had two different call stacks, but each one with a different number at the bottom, a different line at the bottom. So we can see that each of these is unique. But there's something else to be said, and that's that each of these points, and you've seen it as it's descended into that function call, each of these points, it describes not just where we are in the program, it describes not just when we are in time, but here's the important thing, it describes the entire history up to this point. Because when we were at this point, there was no way we could reach this execution coordinate other than by constructing this stack starting from this point and starting from this point or whatever it was. So we can see in this, we've encoded the complete history. Now that too is an important feature of the execution coordinate, and this is something which our debuggers don't produce. And the reason why they don't pronounce is on the next slide. Now what we're going to do now is we're going to introduce a loop. And again, this is still very, very simple code. We're now starting to work with something which is beginning to look vaguely structured. This too is the novelty that Baxter introduced. In 1968, the correct way to do this would have been with the Goto at the bottom. so the test of the bug in the Goto. He said, no, we need to treat these loops as single unitary things. And more to the point, and there are strong technical reasons why he explained this, which I will explain if you ask me, but probably you don't need to know right now. He said, these things are procedure calls. So they're not merely loops, they're not Gotos. When he said that he wanted to get rid of Gotos completely, he really meant it. These are procedure calls. So when we execute it, when we begin the loop, then the thing at the beginning is from the very beginning to the very end of it. We call it line 11, but actually it's that entire space from line 11 to 14. Look at the execution coordinates. Because it's a loop, we can't do it now. It's indexed. So when we start it, when we carry on the execution, we now stack it just as if we're calling a procedure.
Excuse me,
Yes.
just stand slightly more to that side. I can't see the
Better?
stack, yeah.
That's better. Yeah, so you can see that we've got the index on the level to say that this is the first time we've fitted it. And we're now in line 12 as if we are inside the procedure call. And as this continues to execute, you can see, well, you can't see. You can see that that index has gone up to represent each of these. So here are the three basic properties of Dijkstra's idea of an execution call. We need to have the idea of a location in space and time. We need the idea of descent, of tuple, he called it, which is the stack. And we need the concept of iteration, which is what we're seeing here. And he says if you put those three things together, and if you represent every moment in the course of the program's execution, then you have a complete description of when and where you are in the same representation. And we use this. Right now we use this because we can actually point to a position in code and we say, you're talking about here. So a lot of these ideas, even though we haven't got this level of formality, we are using these ideas today. Remember, this stuff is 50 years old. Now, okay. Now what's the alternative? Here is a piece of code, and there is nothing to see on the I'm afraid. This is about the simplest piece of unstructured code that I could contrive. Looking at that, can anybody figure out what it's doing? No, me neither. But that's the point. Now, Dijkstra said that this kind of code is impenetrable for a reason. And the reason is that there is no such thing as an execution coordinate. Now, why is there no such thing as an execution coordinate? Because if we start executing it, we can do what we did before. We can say for each line, we can find out what time it happened. But what we can't do is get that correlation. You see, we're stopped at line 14. And line 14 has quite a lot of instants in time, and they are indistinguishable from each other. And each of them has a different history. So what we can do is we can say where we are, and we can say when we are. But we can't use the same thing, we can't use the same number to represent both. So, Dijkstra's view is that we can understand that. Nobody can understand that. And particularly when you start to get to humongous programs like nearly 5,000 lines, then nobody stands a chance. Okay, so that is the reason why, that's the difference. That's why he said that we wanted to get rid of Gotos, because it's the Gotos which are causing the problems. It's the Gotos which are abandoning this. When you do a Goto, then where you're going to, it doesn't appear. When you've got the code indented in a structured fashion, you can see where the beginning and the end of the loops are. But in this case, you can't. There's nothing to see. It's just random jumping about. It's spaghetti code. And you've all seen spaghetti code, and you all hate it. None of you would ever write code like this, would you? I don't know if you've seen, but there's a bit in Windows, in the real kernel of Windows, where there's this label which says, I can't believe they made me use Goto. I don't know if you've seen it. Okay, so let's just review what this execution coordinate is, because this is important. The first thing is, it is a tuple. It's a sequence of things. And those things are numbers representing locations and points of time. repetitions, and you have the stack. And each of those can be a repetition, or each of those isn't a repetition, depending on if it's a linked or not. So each of those is either a procedure call or it's a link. Make sense? Now, the structured code, the point is that it shows us the location within the code, physical location, geographic location. It shows us the moment in execution time, and it shows us the entire history leading up to that point. If the code is not structured, then we lose those two. We only know the location. Now, this is the important thing to see. There is nothing intrinsically wrong with Goto. Inside your machine, by the time you get down to the native code, there are no such things as loops. There is only Gotos. At the assembler level, frequently there is only Gotos. But that doesn't violate the structure. What structure means is not that there are no Gotos. And it doesn't even mean that you only have a very limited palette of the loop, the control structure. You can have quite complex control structures. What structure means is that we have an execution coordinate, no matter how that is contrived. Okay? Now that's the important thing. Gotos in themselves are not the bad guys. It's the way in which you use them that makes them the bad guys. So, we have Goto, we have synonyms for Goto, we have structured Goto. It's not just loops. Things like return, an early return from a function, is precisely a Goto. It's a Goto to the end, and it's unwinding the stack. Continuing and breaking, again, is a jump. It's a Goto to the end of the loop that it's in. So we're using Gotos all the time. They're just disguised as something else, disguised as something not as scary. Because what they do in this form is they preserve the execution coordinates. So let's now look at another piece of code, which is apparently structured. Nothing wrong with this. We can execute the code in exactly the way that you just saw. Look at the second loop. Now you can see what's happening here. We've got basically two conditions. Each condition has got two paths, but the paths are geared together. So if we superimpose these two, and remember, for the execution coordinate to mean what we think it should mean, these two things, when they're put together, should look pretty much the same. But what we're seeing is that even though each of these lines has a unique moment in time, the moment in time is not unique to that line. So when we say line 19, we know where we are, but we don't know when we are. Now here's the thing, this looks like perfectly acceptable modern code, but in Dijkstra's terms, this is unstructured. In Dijkstra's terms, this is what he was trying to get rid of when he wanted us all to give up our Gotos. Now, remember, this is the day of Fortran, of BASIC. He didn't have anything to replace this with. He could represent something to get rid of Gotos, but he didn't have anything to replace conditions with. But today, we do. So here's our problem. We've lost our history. We've still got our forward. We still can relate a point to time, but a location to time. But what we can't do is recognize and preserve our history. So here is where our problem lies. Now, superimposed like that is obvious, but when we take them apart again, there's nothing in that block to show you that this or this are pathological cases. There's nothing there to show you that those are the things which are destroying your history. But it's quite clear that these two fit together. That if we find ourselves on line 19, we must have passed through line 14. There's no other way to get there. The trouble is that that's not explicit from this view. It's not even explicit from this view. So, I'll tell you what the pathology was, what the anti-pattern was. This is it. It's one condition, one state, one decision, used in two different locations. It does it all the time. What's wrong with it? Well, the problem is it's impossible to keep them synchronized because they're separated in the code. There's nothing to tell you when you're looking at this that there is somewhere else in the code another condition which is up to actions. So that's the problem with that. So it means that people along does some maintenance, then they're going to miss this. You can't keep them somewhere. And in this case, it's pretty obvious to see, but actually there are a lot of cases where these things are discarded, where you've got these geared states, or these geared conditions, and they're not obvious. Here's an example. Let's suppose you're deciding you have a program which optionally logs to a file. So, at some configuration level, you've got a flag which says, yes, we want to log to this file, and we don't. At some point in the execution, we create a log file stream, or maybe we don't, based on the level, not based on this flag. And at some other point in the program, we construct a message, which is our log message, but we don't bother to construct it if we haven't got a log file stream. And then finally, we output this if the message exists, if the file exists, if the flag is set. What's the condition? What are you testing against? So whatever it is, it's been hidden somewhere in the invisible internal state of the program which we can't get to. So what we've got here is not so much spaghetti code as wormhole code. And that is the anti-pattern. Now, why is that responsible for all of our technical things? Well, the answer is, how do people fix problems? How do people fix bugs? You run the program, you wait until you can exhibit the pathology, and you go, okay, what's the wrong value of the variable? And at that point, almost everybody sits around and patch around it, do some default programming, or do some protection programming or something. But the point is that the fix is not to go back and correct the original defect. 99 times out of 100, a fix is to stick a plaster over the actual defect. We're not fixing the defect. What we're doing is fixing the malfunction, which means it's going to come back and bite us again. If I talk about defects and malfunctions, do you know what I mean by that? Anybody not know?
Do you mean there's a distinction between the two?
Oh, yes.
No,
Okay, in that case, this is worth saying. When you're driving your car, and then your car suddenly starts going all over the road, that's the car malfunction. You know the car malfunction because it's a private straight. And if it's happened, then it's almost certainly happened because the component is broken. So there's a fault in the car which was not there at the beginning, but the fault has developed. So you go in and you fix the fault, and now your car drives straight again. So that's a malfunction caused by failure. In software, there are no failures because code doesn't, bits don't rot away, it doesn't work that way. Every time a program malfunctions, it's because there's a design defect. It's because you programmed a fault in so that you created the defect in the code. Now, Fred Brooks, whose book everybody should read because it's an absolute classic, he made the observation that programs of any time tend to have an absolutely constant bug rate, a constant malfunction rate. So, you know, it might be 1 bug per 1,000 lines of code, or if you're a really good team, 1 bug per 10,000 lines of code, or the team I was last on, 1 bug per 10 lines. The point is, it doesn't matter how much bug fixing you do, the bug rate stays absolutely constant. And he was saying, well, why is that? It's because there are times like more defects than there are malfunctions. So what you do is you might fix a malfunction, which is caused by a defect. If you're good enough to fix the defect, then all that happens is that another defect gets to be surfaced. So there's an awful lot more defects in the code than there are malfunctions. And this is what defects look like. This is the anti-pattern which seems to cause most of them. So does that make sense as an explanation of sort of anatomy? Okay, good. Now, let's fix this. Because no real program would write like this, would they? It's much better to replicate the body of the inside of the condition, could be, this is to duplicate the condition. Isn't it? No, it's not. It's a terrible idea. But even that, even if you did claim that that was a good idea, it doesn't work. And the reason why it doesn't work is because, as I said earlier on, sometimes these conditions are disguised. It's not conditions so much as some states that we want to test on. These things, they might be in 2 different methods or 2 different functions, or they might even be in 2 different machines. So you might not actually even be able to get these 2 conditions into contact like this, just because of the structure of the program. So this is not the answer, but we still need to fix that. If we can fix that, then we can fix our reliability problem. Now, I said at the outset that I was making a big claim. I said at the outset that we could fix 90% of our bugs and 99% of our code loss in one step. Does anybody not believe that if we can fix that, that our optimizer fails? Really? Nothing better than I thought. Okay, good. So how do you fix that? Well, it seems to me that the problem that we have here, the thing which really causes this pathology is because we have our condition and our decision, our consequence of decision, in the same place. What we really need to do is to take this condition out, take it out of the main flow and put it somewhere else. You see, that's what we do with the go-tos. We don't put the go-to where we want to go to. We don't put the go-to at all. We give the go-to other names like while or return. But the point is that the actual go-to, the thing that we're going from, the thing we're going to, are now no longer in the flow of the code. It's been brought out and depicted and constructed some other way. So that's what we want to do with this. We want to construct some kind of structured condition which separates the condition from the consequence. Okay? Now, why did I do that? I know, that was just to show you how badly one I've got it. Because the code itself was exhibiting the bug. And nobody noticed, did you? It shows how easy it is. Okay, so now let's talk about the execution coordinate in the terms which we just seen. What Goto does is it destroys our temporal identity. That, you understand, that makes sense. What ifs do, particularly these synchronized ifs, is they conflate the temporal identity. They don't destroy it, but they sort of superimpose it, so you've got two pictures in one or more. Goto destroys history. So does ifs. Goto creates spaghetti. Ifs create wormholes. Now, I'm talking about it as wormholes because what you've got is two distant points of the program which are moving together. Condition goes one way, condition goes the other way, and there's nothing visible in the code to show you that those two things are geared together. So that's what I'm calling a wormhole. And I'm really hoping that you're going to take this out into the world and alongside spaghetti code, which everybody understands, I want to talk about wormhole code, because then this is going to start taking root. Now, what we did in 1968 was we stopped using go-tos and we applied the go-tos to the structure of the code. What we're going to do in 2014 is to apply the decisions from the structure of the code. So what we're going to do is see how far we can get expunging if altogether in the same way that we expunge go-to. Now remember, we can't do that now because there are no languages that will allow us to do that. We need this instruction language to do that. So we're going to have to fake it in the same way that we fake it go-to back in the old days. But we still want to imply this decision structure from the code. And remember, not all go-tos are evil. Even today, not all go-tos are evil. And similarly, not all ifs are evil. I'm not trying to stop you from using them at all. I'm just trying to highlight you to this anti-pattern. Because the anti-pattern is where the problems come from. But there's something else that I want to point out. And this, if you thought I was courageous in my claim, just wait till you hear this. It seems to me that if you go back and you look at the original definition of what an execution coordinate is, then goto doesn't violate that. The only things that a goto can do is either commute the order in which you're executing the last you sort of apart from order and then go somewhere else, or you construct a repetition and you go round and round. The problem is not in the goto. The problem is in if goto. Because it's the condition which is messing things up. Are you guys noticing the pattern here? I have a feeling that the wrong guy has been blamed for the last 50 years. The problem was always this. You had it here first. So, here's our summary. We need a new notion of what it actually is. We need a new notion of what a condition is. And we need this separated idea. What we want to do is concentrate conditions. Instead of having the conditions where we want them to all over the code, what we want to do is to have conditions localized at certain points. And later on in a few minutes, I'm going to explain to you exactly where those points should be. But the decisions should be applied. Remember, in structured code, in loops and in functions, you don't actually say where you're going to. You just say, well, it's brackets, and you just make it. You create a place where you assume it's what you can apply. So we want to do the same thing. Those decisions are consequences of the condition. Whether you do this or whether you do that. We want to imply that. We want not to explicate it. Because it was the explication, remember, which has created our conflation, our time conflation. Okay? We want to separate out those two branches completely and make them imply. We need some new mechanism to replace it. Nobody can write a program that doesn't make decisions. So we need a new mechanism for doing this. And I'm going to give you three, in the same way that the assertion was made in the 50s and 60s that you could replace all Goto with a certain small number of structured constructs, which were whiles and do's and functionals. I'm going to claim that you can replace every use of if in modern programming with these three constructs, and you don't need any more. And I'm going to explain right at the end why I think this is the complete set. So if you can get your head around these, you need never write another one again. Not only that, if you construct your code that follows these, then your bug fixers can't actually introduce this pattern. So you're protected from the code bugs. In the same way that right now you're protected from spaghetti code because you can't even express the Goto anti-patterns. So what we're going to talk about is assertions, which you know about, value-based polymorphisms, which maybe you know about, and dynamic anti-casting and specialized classes, which some of you may have handled before in other contexts, but probably not in general purpose programming. Is there anything that anybody would like to ask now? Is everybody just going, oh, what are you saying? Okay, fair enough. Yes, no, that's an important point. Back in the early days of Goto, people were starting to talk about structured programming, but they didn't have structured languages. So what they said was, follow these rules, and your code will be safer. And to the extent that people could follow the rules, their code was safer. We don't have condition-structured languages. There aren't any. I haven't written one yet. But that does mean that what we need to do is to simulate these condition-structured things using the tools that we've got. So for each one of these, what I need to do for this to be any useful at all is to give you conventional expressions of those, which will work in your program, but which will also protect you from the downstream maintenance. Right. Let's do assertions first. Here is a nice simple code, nice simple program, nice simple procedure. It's a square root function, you can tell that from the name. It's returning a float, you can tell that from the description. But this is unsafe. And this is unsafe because if we present this with a negative number for A, then there is no valid float which can answer that. Now, of course you can take the square root of a negative number, but you can't take the square root of a negative number and call it a float. So either that's wrong or that's wrong. So I'm going to claim that that's wrong. I'm going to say we need to protect it against a negative A. And that is the syntax which I'm going to do. I'm going to say, I want this to be positive, or I'm going to take some action about it. Okay? Now, you can express this as an if perfectly easily. You use assert all the time. Any of you done programming by contracts? Just two? Wow. You should look this up. Programming by contract is brilliant. But in contract terms, there's a precondition. And preconditions can actually be tested at compile time in a lot of cases. So this is an exact reflection of the kind of contract, the kind of precondition that goes on in contract-based programming already. So this is not contentious at all. But There's something also wrong with this, and that is that we haven't said anything about what A is. We actually need to be numeric before we can start to apply that test. So now we've got two assertions describing the nature of that parameter. And you can see what the difference is between them. In the first case, we're saying this is just a fundamental error in the shape of the program. This is the kind of thing that should be thrown to compiler. This one is much harder to throw to compiler because you might actually compute a negative value. So, in the first case, we want to say at compiler, no, you've got something really wrong. In the second case, it's a perfectly normal exception. So I'm going to claim that there are actually several different forms. Okay. The reason I've done that is that if you can test that at compile time, then you should. So this is saying, if you can error at compile time, then do so. Otherwise, throw the exception. Now, what's really important about these is that there is no else. Not only that, there's not even a body. The purpose of this construct is not to control the flow, but to abort it. So, this is something like an early return or a break. This is a get out. Okay? And more to the point, they're getting out without even returning a value. This is saying we are aborting this function. So, remember what our problem with it is. Our problem with it is the branches. So this construct does without the branches. So the if is safe. It's the alternative as well. So this takes away the alternative. 4 different types, I think. We either return a null value, and a lot more about null values. Throw an exception, just kill the program completely, and let the watchdog pick it up, or let your emergency recovery pick it up. Or throw a compile hammer at if you also pick it up. Now, I think this should be standard practice anyway. I think that if you're writing procedures and you're not guarding all the parameters, if it gets through the first set of checks, then you should be prepared to finish it, honestly. So I think this should be normal practice in any program. But what I'm doing is I'm making this a formal part of this theory. I'm saying that this is one of the forms of condition which is legal. This is a specific assertion which is designed to avoid the process. Now, we don't have that kind of assertion. Most assertions, they die at runtime and all they do is abort the program. So what we need to do is simulate that using the language constructs that we've got. It's perfectly simple. It's just an if. We don't have the error version. It's very difficult to construct an error at compile time using this, but again, with suitable compiler tools and with good languages, like I will do a degree of runtime compile time checking, then you can get a lot of that protection. Okay, so that's the assertion. Any questions about that? It's simple, isn't it? And you can straight away see how to protect the error. It's also a terrific documentation. You can come along afterwards, a list of assertions at the top they tell somebody exactly what this procedure is expecting. Okay. Now the next bit is about value polymorphism. So I want to talk a bit about what value is. Again, we'll start off with a really simple piece of code. This is the kind of code that everybody sees with a language program. Listen. Now the reason for putting that up is that this is the kind of polymorphism which we are used to seeing in modern languages. You could say we've got different types of different functions which we would call depending on the type of the parameter. You see there's a hell of a lot of constructors. Most languages have polymorphic constructors, even if they don't have polymorphic methods. Languages like Smalltalk, they they don't even place the methods inside the classes. They're all outside. They're polymorphic on every single parameter. So what I'm showing you here is not anything which you haven't already seen before. This is very conventional stuff. But does anybody here know Haskell? Okay. Again, 2, 3, not many. Haskell wouldn't write it like that. Haskell would write it something like this. And then I've done some violence to Haskell syntax to make it accessible. But what's going on in the Haskell is that it's polymorphic, not merely on the type, but also on the value. Okay? So we're saying that 1 is a more specific thing than a mere number. So if we're presenting it with a number which just happens to be 1, then that's what we do with it. And then only afterwards do we switch over to the number. So far, so good. Incidentally, in Prolog, does anybody know Prolog? It's the only control structure 1. Excellent. It's fun and completely useless, but it's a great fun language. But this is the only control structure. There is no other. So again, it's worthwhile having a play with Prolog to get a sense of how it thinks. So back to our old thing. How do we take that kind of thing and express it in these terms? Well, that would do. Now, at one level, we still have the problem in this that we're replicating the inside. So this is not ideal. But you can see how this works. What we're doing is we're saying the actual condition, it's concentrated here, possibly here. But we've separated the condition from the branch. If we find ourselves on this line, well, actually, we've got our history back. We've also got, our entire execution coordinate is as it should be. It's correct again. So you can see that this is getting us a long way towards the kind of structure, the kind of coherent execution coordinates that we really want to have. Again, I would say that looking at that code, if I was having to maintain that code, that seems to me to be a lot easier to maintain than that. This is the other thing, easily extensible. Okay. Now, in practice, modern languages don't have any polymorphism. We have to take it. So the example of the Fibonacci number that you saw first is actually the correct way to do this. But actually, the way it looks in practice is the very first thing you do is you'd have a lot of conditions where you'd have one big switch statement. And then when you got down to where you were going, you'd have these blocks of text. So instead of placing the condition on the parameter, you'd have to place it in the body of the code. But we place it at the highest level, exactly the same place that you put the assertions. Now, it's not ideal, it's a bit of a fudge, but it's the best we can do in modern languages. But it will give you the protection that you need because you are being explicit in one place about what your decisions are, and you're explicitly not spreading them out over the code. Now, this is another way of doing it. We can have specialist downcasting constructors, and we're going to look at these in much more detail because the technique that I've just shown you actually really comes into its own when we do this. So, for example, if we have a class for money, which, if we instantiated something, a plus money object, and we only instantiated it with a positive number, if we can guarantee that, then what we've done is we've concentrated the condition in this constructor, in the point at which that is constructed. So again, what we've done now, by doing this, and again I'll show you this in more detail in a moment, is you take the condition completely out of that flow altogether, and you put it somewhere else, where it's actually very visible. And of course that is the alternative. Use a method called really helps us to do it. Okay. Now let's take that principle and really leverage it up. What we have here is a very simple piece of code. You can see what's doing it. It's simply aggregating. This is the kind of thing that you see in particularly modern languages, languages like C#, which are based on pointer semantics almost entirely. Even though they don't expose the pointers, the underlying semantics is very pointery. Oops. Now, in the constructor, we may or may not set a value for little class, for C. The point is that having set or not set it, then the state of that variable, the state of that field, is there in the class ready to be tested. But it means we can't use it, because every time we look at it, we need to know whether it's there or not. Okay? This is code that you see all the time. It's endless testing. You miss one, and you're in trouble. And again, this is something that I've found an awful lot of bugs. These uninitialized variables, people have bad dreams about uninitialized variables, and yet, here it is, disguised away such that it's very hard to see. I mean, except that it's tiny code, so they're easy to see like that, but in a real program, it's much harder to see. Now, the reason why that's confusing is because I think that there's something deeply wrong with the semantics of what that was saying. You see, if you were to write C as 4, then what we're saying is that we're instantiating it to, or we're constructing a little class from the value 4. But when we say it's null, then we're saying it's null. We're not saying that we're instantiating it from null. And I can't see any reason why that should be different. That seems silly to me. If you've got a variable which is proposing to be a little class, it should be exposed in the little class interface. I can't see how anything else makes any sense. So, I would say we should go with the second interpretation. A null object would expose the interface, but a null pointer has no interface at all. A null object, you can just use it. Just talk to it. But a null pointer needs guarding on every single use. The null object can be checked at compiler time. You should be doing your checking. A null pointer, you have to check every use at runtime, which none of you should be doing checking, because by that point your program is already starting to expose the defect. It's already malfunctioning. So let's go back to this code. If we represent C the way it should be, then we can do all of that. And that seems much clearer. Does that seem clearer to you?
You just put that back.
So that's how it was. But since we're now saying that C is now not null but a null object of class little class, that test is unnecessary. Now, here's the thing, if you are doing something, in the previous case, if you're doing something based on C's non-existence, then why can't a null object do exactly the same thing? Now, I have been arguing for null objects for years, and most people, certainly compilers, seem to be fighting me because they seem to really like this idea of null pointers. But I don't get it. I really don't get it. I think that should be the absolute normal way of initializing fields. I think that there's no excuse for creating nulls. And I really feel strongly about it. I feel really strongly about it. But once you're at that point, once you're saying that you have this object and it is guaranteed to expose the interface so that you don't have to do the null testing, then you can start leveraging that. You can do all sorts of things with that, because what you're saying is the condition is part of the initialization. We either initialize that to be a null object or we initialize it to be some other non-null object, and that's the point at which the condition is defined. Remember, I wanted to separate out the conditions from the consequences. This does exactly that, because the condition is at this point and the consequences are at this point. Okay? And in fact, the consequences are explicated inside the classes. So, remember I was talking about implied conditions. We want to imply the conditions as much as we can. Every method in every class has an implied condition if we are running in the context of this class. And you know this, and this is not challenging in the slightest. But we can leverage that. We can say this is how we want to explicate our conditions in real code. So here is a notation which I use in planning an awful lot. Again, there are no languages which have a notation like this. But what we're going to do is we're going to construct, or we're going to talk about a class, which is, in this case, an abstract base class. And it's abstract, so we've made it constructed private. And we now have a bunch of separate implementations. So we've got options now. If we're not prepared to honor this, then each of these is representing a different kind of constructor, a different kind of object, a different kind of behavior, a different set of consequences based on the decision which led to these. If we want, if we try and create something which is not of that class, so if we wanted to create something based on a point, for example, there is no little point. So it's going to fail at compile time. So we've got a great deal of protection against conditions which we haven't promised to honor. But we need to get from there to there. When we want to create an object, we need to figure out which one of these constructors we're going to use. Because what we don't want to do is make that the responsibility of a calling object. We want to imply that. So this is how we do this. What we have is a constructor whose syntax says we are now going to defer to one of these subclasses. Now, look at how this works. The caller has said, I want a little class object, as in the previous case, and I want to initialize it with null. So this is handing back a little null. It still is answering the little class interface, but it's subclassed down to a little null. So all of the behavior inside little null is defined inside that class. All of the consequences of that decision are inside there. And nowhere else, because they are precisely the consequences of that choice. And yet at the calling level, it can't see the difference. All it knows is that it's got back a valid object which will honor that interface. So does that make sense? I'll say it again. We want to separate out the decision and the consequences. There are the consequences. Here is the decision. And at the calling level, at the point at which we actually created a class object, that's the point at which we say, this is the actual behavior, this is the function, this is the reason for calling. So we've got these three things explicated separately. Does that seem clear to you?
Slightly different to a factory.
It is a factory, in fact. The reason why I write it in those terms is because, sorry, I made it from the line. Who asked? Right. The reason why I'm writing it in those terms is because if you want to construct a little class and it has a public constructor, then you'll say new little class or something like that. If you want to call a factory method inside little class, then you'll say little class method. Now it seems to me that syntax is deceptive. If you're asking for a new little class, then it should be perfectly acceptable for little class to hand back a subclass of itself, because that's fulfilling the contract. So this is a factory, but the factory is embedded in the constructor itself. Now today, and this is what's on the next slide, today we have to do this as factories, but we don't have any option. But when I'm sketching code, this is the notation that I use, because what it means is that this has become the constructor and the factory and the interface specification all in one, which I think is a more clear and a more honest way of expressing what a little class is. Does that answer the question? Okay.
Another question?
Yes.
Have you explored this technique with dependency injection containers?
Sorry, I
Have
didn't
you explored the use of this technique with dependency injection? With dependency injection, you delegate the construction of your objects, so the container can make decisions for you.
Yes. in fact, in some, and again, you'll see it on the next slide. One of the things that you can do is you can actually take this decision as to which subclass you're going to call at the point at which you construct it. But I do think that's a fudge. I think that it should be down to the constructor itself to understand which of the subclasses it's going to actually expose. Does that answer your question?
Okay, other question. Is this now a pattern to avoid working with null objects, or with the problem that is right in the beginning, there are some those over and over?
Yes.
Well,
yes. You see, I'm claiming here that...
two patterns in one pattern.
Yes.
So a null object pattern and something like the inversion of control pattern in one pattern.
I'm claiming that they're the same thing. I'm saying that the problem that we saw by using those, by having to test those null fields, is precisely this problem of hidden state, precisely this problem of weren't null code. If you have it all combined into the point of construction, then you don't have weren't nulls, because it's strictly down. All the consequences are strictly bound by that class description. Okay, so it doesn't matter whether it's a null object. I mean, you might forbid a null object at some point. You might say it doesn't make sense. We can have numbers, we can have strings, but we can't have nulls. That's fine. But so long as it's initialized to something which is prepared to honor a stated interface, a defined interface, and that's what we're trying to accomplish. And what we want to do is hide from the container object the actual details of how it's delivering them. I mean, that's the fundamental thing of object programming, isn't it? It's hiding. So I would say they're all the same thing. Remember, what we started from was these synchronized ifs, and we're using this method to remove those synchronizations. Yes?
When you say that the null object should honor the interface, well, that makes sense, but I have a hard time imagining that the calling code is always completely, I mean, that it doesn't matter at all to the calling code whether the thing that you're working on is a null object or not. I mean, typically it has an effect. It could have an effect on what you're going to do afterwards, etc., etc.
Okay, let's take an example of that. How many do time? Completely time. Let's go back to the example of error logging, or just log. We can create a file logging object, and we can initialize it either to a null or we can initialize it to a name stream. And that object will hand back either a null file or it will hand back a fully constructed warm null stream. Okay? We can then start sending messages to it. And once we've completed the sending the messages to it, we can then connect, we can flush it. Okay? Now, if it's a stream object, we go to the message, and then we flush and then we go to the log file. If it's a null object, it just eats it. Nothing happens at all. There's nothing behind it. The functions just return. Now, if you've got a null object, if you have a null pointer object, if you have a null field, then you have to know what you're doing in the case that it's null. I mean, if it's what you want it to be, then it's got to do something. If it's the null that you don't want it to be, you have to do something else. So, either way, you're entering that you have an intent in mind, and you might have to accept a very thin or null version of that intent. But at the point at which you're entering, at the point at which you take the decision, you do have that intent in mind. So that intent should be explicated in the interface to whatever the object is that you're dealing with. So that's what the null object does. It says, this is what we promised to do. This is the interface that we expose, even if in this case what we're going to do is do nothing. Does that answer the question? Or would you like to explore that more?
To some extent, yes. I think yeah.
Okay.
So following on from that, if your code did require an object that wasn't null, I assume you would then assert that fact. That's where you would use the assertions.
Yes, because there is an implied assertion at this point that if we didn't have a null parameter to construct with, the constructor would fail. And in fact, the constructor should fail at compile time, because that's where the assertion is implied. You happy with that?
Yeah.
Okay.
In your example, you obviously had a logging thing which only took inputs. If you were getting outputs, what is the...
What, from a log file?
No, from an object, you have a null object. A null object
And the
that
file?
you return a value.
And the file?
Other examples?
John, you know what? This is your from the line. I've got the solution.
I don't know, I'm just thinking of in general cases, very often you're not just sticking things into an object, you're not just sending messages, sometimes you're getting stuff back.
Yes, you are.
If
But
I've
there
got a
should
null
be.
object and there's no value now, should that be returning more null objects essentially? So you kind
Yes.
of like a chaining of
Yes, it should be
null
returning
results?
more null objects. It shouldn't be returning null. It shouldn't be crashing. It should be returning what, for want of better words, is the most trivialist thing that it could possibly be. So if you have a file reader and you ask for a null file, it'll return in the file immediately. If you ask for user input, then it'll return in the file immediately, and so on. If you have a queue and the queue's empty, and you dequeue something off it, then it's moot whether that should be an exception or whether that should be a null object. But if you choose to return something, so if you've got like lead-in on the queue, then very definitely those should be null objects, not null pointers. Because somebody wants them for some purpose, and what you don't want to do is to have that somebody else continually checking whether it's null. So if you're returning anything, it should be null. It should be null objects. Sorry. Okay. Any more questions? We're back here again. Now, what does that look like in this model? Well, what we're going to do is we're going to take that number, the B number, and we're going to turn it into a money. But we know that we want two different kinds of money. We want this different behavior depending on whether the money is money. So here is our complete set of classes which will handle that. We have a plus money and a minus money, which between them will impact how we want. And then we have one of these decision-making constructors which will select from one of those. And then the base constructor is still private, even though these are going to have to refer to the base constructor. It's private, so you can't just make a money. Now again, out of that, it seems to me very easy, very straightforward. It's telling you what you need to do. It's concentrating the decision in one place. It's concentrating the concentration. It's concentrating the consequences in another. But more interesting about this is the body is now in here. Because what we're doing is referring back to the base class to handle the body. So the problem in the first version of this we've now solved by having one of these deciding constructors. So does that make sense? Is that clear as a piece of syntax? Okay. Now, you asked about how you handle this as a factory. You have to do it as a factory. In practice, this is probably one of the hardest ones to actually express in real terms. So you can do it as a factory. You could create a factory method and call it explicitly. It's not nice, but at least it makes clear that there's a decision behind it. You can expose the subclasses directly. I don't like doing this either. It's really ugly, but sometimes it's just the easiest way of doing it. Again, if you've got these things in place, then you're telegraphing warnings to people that something's going on. You have at least concentrated the decisions and the consequences separately. And you can always guard these with assertions to make sure that people don't misuse these subclasses. If you're feeling strong, you can pre-compile. You can actually look, you can construct, you create a name downcast one. You can do this with any language. This is really simple syntactic modification. Something like an org script. But you can recognize a class as being downcastable, which means it has one of these decision-making conditions. And you can change calls to constructors into calls to the factory. I mean, the script is going to depend on the language that you're working in, but this kind of thing is literally 20 lines of code. So, any questions at this So let's wrap up. We're a bit early, and I'm sure there's going to be plenty of questions at the end. But Goto is harmful. We know that Goto is harmful. It's beyond any doubt. It's been what we've known for the last 50 years. By the way, does anybody here doubt that? Okay for that. I do. Actually, Goto was not the problem. It was always the if that preceded the Goto that was the problem. We have been blaming the wrong guy. So we need to address ourselves to that if. If Goto creates spaghetti code, and spaghetti code is unreliable, does anybody doubt that? Good. If create wormhole code, and wormhole code is unreliable, does anybody doubt that? You're not just scared of me, are you? Okay, the antidote to Goto was flow structure. This has been established for 50 years. We know what the flows are. It's been studied mathematically in rigorous detail. I claim the antidote to if is decision structure, condition structure. Let's explain what it is. Structured languages replace Goto with things like for, while, more recently throw. That's also a structured construct. A decision-structured language is going to replace it with asserts, value polymorphisms, and those dynamic downcasts. And that's all you need. In the same way that for and while and throw is all you need, these are all you need. Okay, be careful. You can do structured programming with Goto. People did for years. People still do. If you're careful, you can do decision-structured programming with ifs. But you've got to be careful. And you might just have to wait for language technology to catch up with them. Okay. Now I'm going to leave the takeaways on the screen for now. I'm now going to tell you what I think is the clincher. I got started programming in APIs. I have spent time creating medical systems. High quality, very robust programming is in my blood. And it has been since I started, before most of you were born. I didn't know how I did it. I just knew that I was good at it. So, one of the things that I did, I was working on a program. It was about 25,000 lines of dense C++, heavily memory managed C++, the kind of thing that normally would be a hive of defects. In the course of the development, this is before it was finished, it was fingered for defects for malfunction 6 times, and every one of them turned out to be a false call. This program has no defects even in development. So, after having done this review, I went back and had a look at my code. And what I found was that in 25,000 lines of C++, there were 6 naked ifs. All the others were in one of these forms. I thought, okay, that's interesting. So let's see if I can generalize this up. And so, for another project, I wrote a compiler in PHP. Don't ask, that's a whole different story. It was only a simple compiler. It was 2,000 lines. It took me a fortnight. But the point was, could I write it in a completely inappropriate language? And could I make it reliable? The only bug in that code was one that was produced by a contractor. And it came out instantly. So this stuff actually works. So then I thought, all right, let's go back and have a look. So I went back into other people's code bases. I started looking at open source projects because it's easy to see the history of the open source projects. You know what? I could predict every single defect and every single bug. I could see where bug reports were coming in because you can see these anti-patterns appearing. And they localize where the defects are. You can predict what the malfunction is going to be because you can spot them. So, this stuff works. It predicts where your defects are going to be. And if you do it right, you genuinely can write clean code for the first time. And the funny thing is, it takes less time than doing it wrong. Okay, so here's the takeaways. If it's not the bad guy, but misusing this anti-pattern, this anti-pattern of synchronized bits, this causes more bugs than all other causes combined, and it causes almost all of your technical debt. And this is true for every live project I can find. This shouldn't be news. The theoretical foundation of this has been known and studied for the last 50 years. I have no idea how it's taken us this long to notice, but it really has. The fix in the 60s was to create new classes of language. We need new classes of language now. If we have them, our programs will get better. But for the time being, we just need to be careful and program hygienically, program in a conditioned structured style. Now, this is the reason why. This is what motivates me to stand up. I agree, I'm terrified standing up saying this. But this is the reason why, because time after time now I've measured this. This is bug pathology and it's caused by the semantic memory. And there's no need for it. Okay. Any questions?
How did you measure that? How did you get this data, and can you get it in an automated way in the code base?
It's hard to get it in an automated way. I have to admit, if I put more effort in than I could. But the way I did it was that I was looking, we had pretty good, I mean, even if we didn't have good code control, what we did have was pretty good tracking. So we were able to look at every single bug in the bug list, and then we were able to trace it to the check-in, which was purporting to fix it. Now, when we did that, what we could see was either the fix that, well, we could certainly see the fix that it was made, but some of these, they were introducing more of these, which meant that we could follow them down through the line. We could see when the same lines were implicated in subsequent bugs. But the other thing that we did was that we took a sample of them and we eyeballed them. We said, okay, well, stepping back, knowing what we now know, how should this have been fixed? And what we found was that, many times things that were fixed with another condition, actually, they were in the wrong place. And should the defects, had they been able to rewind time in the debugger, they'd have seen the problem appearing much sooner. And in fact, it's one of the tools that we need. It's very hard to find debuggers that will rewind time, but it's because we don't have this sense of history in the execution tool. But if we could do it, then it would be much easier to rewind to the point where it went wrong. But to be fair, it did require a degree of eyeballing, and it's hard to come up with an absolutely categorical type of this, that type, that type. So it did require a degree of judgment. But I invite you to try it for yourself. I mean, you've all got code bases which you like. Go and have a look. You can do your own investigation. You see what sort of code are there, and you see what the root causes are. And I bet you'll find these all over the place. Yes?
In functional inspired languages such as Scala, there's a construct called maybe,
Yes.
which embodies the notion that the value can be here or cannot be here. Any thoughts on that or any experience?
Can you tell me what you do with it? I have to admit, I'm not familiar with it.
Well, the thing is, you can build these modern chains which are agnostic to the fact that the value is here or not. So in the end, you end up also removing all your keeps that way.
So what it's saying is that if there's a null value there, then don't do anything with it. It's sort of like a get out early.
So typically what you would have is, let's say you call a service and you ask it for a value, and then you do dot select, and you apply some lambda to it. But this lambda would be applied only if the value is here. If it's not here, nothing will happen.
Okay, and that's called maybe.
That's called maybe.
I
It's
really like that, but I think it's 5 letters too long.
It's actually,
for the reasons which you've just seen.
when you use it, it's hidden. It's just because you build these functional, monadic chains. And
I'm looking into it. It sounds interesting.
it's really easy to implement the C# and we're having
Okay.
quite a lot of success with it in our projects.
Yes.
So more specifically, the problem is the else, not the maybe, and you're applying the same, in that case, what you would do with the switch statement.
Actually, the else makes it worse, but the problem is in the if itself. The problem really is placing a condition next to its consequence. Because when you do them close together, if there are more than one consequences, you can't separate them. So this is why, when I was talking about the assertion at the beginning, the value in that is that there is no block, there is no consequence. You're escaping, you're getting out. But and that means that there is no possibility of duplicating that condition, because when you get further down, then there's nothing left to you, that condition is now gone because you've escaped from the function. So getting rid of the else will help, But you can't write a practical program if you get rid of the them and not the else, because all you have to do is put in a complementary condition, and that's what else means. You still lose your sense of history because you've written stuff a program. You don't know if that branch has been executed or not. Because you can't regard it as the same kind of procedure as you regard it. For mathematical reasons, it doesn't work in the same way. So it helps, but it's not enough. You need to separate those
So
two.
when you use if for business decisions, not articles, standards.
Beg your pardon?
When I use if for like a domain, split my domain logic, and not for articles, that's the problem.
Right, but it's the misuse of the pathology. If you are dealing with a problem whose fundamental nature is a decision sequence, say a decision tree, then go for it. Explicate the decision tree. In fact, I would even be very interested in exploring specific decision tree languages, because there's all sorts of consistency checks that you can do on that. If the nature of the problem is decisions, that's fine. If is not the problem, it's the wormholes that are the problem. Is that clear?
Yeah.
Okay. Somebody over here. Yes.
In your example, you have sort of a money value that's a naught or greater than naught. What happens
I'm
if...
sorry, I'm coming close. I can't hear.
in your example, it's very simple, a positive or negative number.
Yes.
But if you had, in different parts of your code, you wanted to do different things for different values of the number, maybe a negative bank account value, you did printed in red, positive, you did something else, but if it was greater than 10, you did something else, and greater than 100, you do something else. You'd end up with a lot of those classes.
Yes.
But for the case where you were just doing positive, more than zero, you'd end up duplicating that line of code in lots of different places.
I think this is a very similar problem to the one that was over here. He was saying that his problem is like a decision tree. I think that you're saying the same thing, that what you have is this long decision tree. Once you've taken a decision, then if you can then commit to that decision and no other, then that's not an abuse of the if. So I'm not suggesting you can necessarily do without them. But if you've got something, I'll make up an example, I don't know if it's your field, but if you have a case where a negative number can't be credited to account, a positive number can, but a positive number greater than 10 starts to attract interest, and a positive number less than 1 incurs a charge, then actually it does seem to me that what you're talking about is different species of credits, and I would want to subclass them. Yes, I would downcast it that way, if it were me. Because somebody, somewhere in the decision-making process has named these things. They've said, this is a high-value credit, or this is nickel and dime credit, or this is just silly, you can't do that.
Haven't you increased your the number of locations you need to go back and correct a bug that you started off with your, for the case where you were doing something just because it was positive bank accounts? I've now got to replicate that code fix in every one of these classes that happens to have a positive number.
No, you've got the code fix in the superclass. They don't all have to be descendants of the abstract base class. You can have a whole dependency tree there, which would actually replicate the decision tree. Okay, right. Sorry, I have some other questions. Students? No? That's all completely clear. Wow, the really well. Okay, just
One more question.
okay.
The rules engines help that all conditions are checked simultaneously, as opposed to being additional branching.
Sorry, I'll do that again.
Rules engine.
That's such a
Rules where you have the condition and all the conditions have to be true
I'm not sure what you're asking, sorry. We have that assertion mechanism right at the top.
Yeah.
And the purpose of the assertion is to protect the function against misuse. Okay. Now that is precisely a sequence of gates, a series of conditions that you have to get through. If you get through the gates and you might be this way or that way, then that's what that casting construction is for. What are you asking me that's not covered by those?
I'm not entirely sure, but you're familiar with rules engines?
No, not really.
Right, well,
Uses validation manager. So
yeah.
it's sort of not there for
Yeah.
what Jules is talking about.
Yeah.
So it's kind of validation stated. The initial state of the software is the rule and
Okay.
the checking of
So what sort of rules is it applying?
some validation.
Tends to be business law.
Oh,
Yeah.
right. In that case, I would say that I would agree with you. I would say that that's it at the level above it. What I'm looking at here is something which is specifically about code hygiene. It's at a code level. With if you've got the wrong business logic, or if you've got meaningless business logic, this is not going to protect you from that. I agree you're going to need something else from it. The problem is not that the business logic is defective. The problem is that your code is defective, and that's what this will correlate. I think that's the correct answer for that. Are you okay with that?
Yeah.
Okay. Any other questions?
Question about the accessions. Do you disable them in production code or do you leave them?
Yeah.
Because if you leave them, then the project will just fail. And if you look at the product, might misbehave, but maybe it will
Okay.
fail less, I guess.
Right. I don't believe that's true, actually. Remember, there are 4 species of assertions. The assertion which ends with compiler error, well, that, of course, you need one unit. There's an assertion that ends with a null object being returned, or a trivial object being returned. So that means, well, we're trying to do something, but we have this is the best I can do. There's the assertion that ends in an exception. Well, you should have your exception checking on. If you made it do something that it can't do, the malfunction's already happened. You're now cleaning up. Well, you have to clean up. Unless the assertion that ends in a die. Well, if you're dying, if you're killing the system, if it's so messed up that you're killing the system, then again, the malfunction's already happened. You're in a complete mess. If the sanitizer's not catching it or the watchdog's not catching it, then you have to leave it to die. But I admit that die is the most extreme thing, but you should be able to catch it. If you care about the reliability of the system, you should be catching it at some point before you bring the whole system down. If you have got this malfunction already happening, then it's insane to keep going. I mean, the first rule of holes is when you're in one, stop digging. So the assertion gives you a means of doing that. This is why they introduced exceptions in the first place. So I do think that it's a valid thing to do in response to a failed assertion, to throw an exception. Present assertions which kill the code, I don't think do have any place in production code. But the reason why I used the whole die rather than kill or anything like that is because I do expect in hardened code that there's something there to catch it at the basicest level to reconstruct the system. So you've got to do something. What are you going to do? Make it worse? You can't do that. So no, I think we need to do it.
Well, so in our reading lines of code, let's assume randomly that 1% of that is condition checking.
Yeah.
Do you have 25,000 classes for every single instance of that? You say you use time that you don't put anywhere near.
You shouldn't have anywhere near that. Because what we're seeing is lots and lots of repetitions of the same conditions.
Presumably you still have thousands of lines, because not every condition is going to be repeated, right? All sorts of different conditions.
In this 2.5 million lines of code, I can't even begin to guess how many actual classes we have in that. But there were screens of them, just because of the way they constructed the code. I'm not scared of lots of names. Big code like that.
I'm not scared this is a system.
By the time you've got the things compiled down, then actually taking out these conditions, concentrating it on the constructors, which I think is probably the most valuable technique that we've talked about. Taking out all those conditions, taking out all the alternative branches is going to reduce your code. You might get a larger namespace, but the machine doesn't care about that. Your actual code is going to shrink and go faster. Okay. Any more?